choose store automatically. Because when they show us, you did the authentication, and when you wanted to add events, you chose and then you should click.
If anyone wants to see posters of example projects from the last couple of years, they're a bunch up front here. They'll be up here until class starts, and then after class you can see them again.
Hi. So, quick question. So, this
Here is my screen.
so, what was the
So, which, there's some plots.
just the first two? Oh, sorry, the word and
So your your runtime is basically linear. Okay, so good. So I just want to make sure you are cognizant of the runtime for other people. I'm not forcing you to have superficial outcomes, but I want to be able to once you start taking away to be able to point to it.
You know what this is asking?
Gotcha.
I was confused because it took me 5 hours to generate the simultaneous numbers. That was like, so I was thinking,
Yeah, it should be
Randomized?
someone else talking to said it took them probably 70 seconds.
This
So you might be able to do it faster. So,
Six?
yeah, so.
All success.
Yeah, so. Yeah, it's fine. So I'm not forcing you that. I hope you actually discuss
For this one, what I did was I set like 10 bits, 10 random bits. So for this one, I took the binary value. I took the binary value of the, and I did random bit 10 times, and I took the binary value of that and just added 1 to it because 0 all the way up to 10 bits. That's actually 0 to 10 bits. So I add 1. That's okay.
There'll be a place in the report where you say,
Using random bit. Oh, the one I'm already using? Can I just say to ignore? So the probability of it.
see all the questions.
This probability how much.
So I just need to say what the probability of failure and what the probability of success. And that's it.
You should have an algorithm that has
So all I have to do is just specify the probability. Yeah, okay. That's all I have to get. So I can just say use the same algorithm as A for the probability.
but there's some numbers more than one.
Yeah, so that's the probability of failure. And that's
And when we got
Yes, you need to figure out how to
redo it.
so they see it. Yes, we can so if no one else I'm
So you're using the same?
but still, they have all those in 1 minute.
I just don't understand what the difference is.
But compared to what,
Oh, how many times?
like compared to other EG studies, like
How many times I should call?
I don't think so. Because you figure the current penetration of EG
9? Well, if it's, but that won't include
current. So if you say it takes 2%, it takes 5%, then that means 20 times 57.
Mary, everything else set for swimming?
No, it's 1,000. Right, so yeah, 1,000.
So welcome everyone. So I'm your instructor, Jeff Phillips. So sorry I wasn't able to be here last week. But hopefully I'll be here the rest of the lectures for this semester. So since I wasn't here last week, I just want to start to see if kind of very quickly review the class outline and see if there are any major questions about the homeworks or the project. One announcement: there's one change in TAs. So Jingwan, who kind of oversaw the first lecture, was transferred to another class, so he will not be one of the TAs. But we have another TA, so Sanjeev Sandeep. So if you can just stand up and say hello. He was one of the very good students in the class last semester, so he'll be around as a TA. His office hours, if you can see him up here, they'll be on Tuesday, 10:30 to 12:30, all right, so they're still on Tuesday. They're at a different time on Tuesday. So if it's not too late to kind of change when the office hours are, if none of these times work for any of you, please let me know. So Yang Gao, also up here, he's going to be hosting some form of occasional remote office hours as well. So if you're not able to be here in person on campus very often, he'll eventually post some of those. But those will mainly be like the week before the homework is due. So I'll announce some other. So we may extend some of these hours every week a little bit before the homework is due. All right. Because I know that's when most people end up going to the office hours and doing the homework. Some people have finished the first homework already, which is great. It's a good thing. So if you haven't seen it yet, I posted it since the last lecture. It's linked off of right here. If you click on this link, you'll see the homework assignment. It's all about kind of experimenting with these hash functions that Sunipa talked about last week on Wednesday. Okay, and so this is meant to be kind of like a primer for the rest of the class. Okay, so we're going to kind of see some like randomized algorithms, and you're going to have to deal with them, and you're going to plot some stuff, and everyone's answer should be a little bit different, right? And we'll be able to, the TAs kind of know, and I know what the answer should generally look like, and we should be able to tell if it's a correct answer or not, even though it's not like exactly the right answer that you put into some form like you might have gotten for some algorithms class. Okay, so this will be kind of like a simple example of some of the things we'll see in the rest of the semester. The hashing as well, I want to make a quick note of this. The next assignment will be using hashing again, but dealing with documents and text. And so the next few lectures are going to be about how to be dealing with some ways for dealing with large documents and dealing with text. And we're going to be reusing some ideas from hashing that showed up in the first assignment. And so some of the things that you'll implement in the first assignment will kind of be reused a little bit if you do them the right way in the second assignment. Okay, so I'll try and post that in the next roughly week, the next assignment. And you'll be able to start on that within the next week or so. You may not have everything needed for it just right away. Okay, and I'll make a note about hashing when I start in the lecture as well. Okay, the other thing is the project. Okay, so remember that this class has a large project component that is worth 45% of the grade. And it's usually like a lot of fun. You get to dive deeper into some topic, more so than we cover in the course. And there's a bunch of deadlines throughout the semester, right? So this last column, and if you click on this on any of these links, it goes to this long proposal document. I may need to make a couple small updates to this, but it's pretty much in place. Okay, so the proposal is due January 31st, so that's coming up in a few weeks. So I don't expect you to kind of completely know what you're going to do, but I want you to really start thinking about it and write something quick down just so you form your teams and you have some idea of what you're going to do. There were some example posters up here we had before class, and we'll have them up after class, and I'll try and bring them the next lecture as well. This is one way to get an idea. I also link to a lot of data sets up there. Browsing those data sets or other things you find online is another good idea to get ideas for projects. But the best projects come from when students bring their own ideas, stuff I wouldn't have thought of on my own. Something you have passion about, you have a hobby where you end up collecting data and you want to analyze it. Like someone did something with analyzing routes of like people doing hang gliding. They're trying to cluster routes for hang gliding. I wouldn't have thought of, I didn't know this data existed, right? So these are the kinds of the coolest projects, I think. Okay, so feel free to ask me lots of questions about your project, bounce ideas off of me, and we'll try and do this feel free to do this as much as you want throughout the semester. That's the best way to get a really good project. Okay, so any general questions about organizational structure or the first few assignments in the course? Yep.
So as far as the project goes, what order of magnitude are we talking in terms of sort of the minimum data set necessary to do valuable analysis work?
Yeah, so it depends a lot on what sort of technique you want to explore. It'll be good to bounce stuff off of me, but there are some techniques we'll talk about which really don't really work until you get to really big data sets. Where other ones will work on data sets with only like a few hundred points. You'll start to actually see meaningful structure in them. So a lot of the text data set, that things need to be pretty big before the techniques we talk about will give useful results. Where clustering, it could be a lot smaller generally. But it depends within each topic. There are techniques that start working on smaller data sets or need much bigger data sets. So it'll really depend. Feel free to send me email, come find me before, after class, office hours, those are great times. All right. Okay, so let's talk about, so I first want to make a quick note about hashing. All right, how is this? Is this, if I write at this size, this is legible for everyone? Okay, so Sunipa talked a little bit about hashing on Wednesday last week, and I wanted to clarify a couple points. There were three things she talked about. One was this SHA-1 hashing. And so this is indicative of like a built-in hash function to a language. And so this is the recommended kind of way to do it. It'll just be easier for what you do in the course. And the SHA-1 is not the only thing. This is kind of a cryptographic hash. It was meant to be like a function people did not know how to take the inverse of. And it works effectively really well as a hash function. But the nice thing about these is that you can have some built-in hash, say in Java, and you can concatenate, say, some salt, and then some input, and this will map to some domain M. And a lot of these built-in ones, they can take in where the input here is a string. Okay, so for the first assignment, this won't make too big of a difference, but for the second assignment, you're going to need to pass in strings here to do into hash functions. And so the built-in ones will make this easier. There are ways to kind of do this mechanically if you were to do something like, the multiplicative hashing. So this multiplicative hashing is basically the easiest way to build something yourself, right? So it's going to be a floor operation of M, which is the size of the domain, times the fractional component of X times A. So A is something deterministic that is used to define the hash function, but you choose this randomly, right? So the hash function is fixed once you choose A. It defines a hash function. We're going to be talking about algorithms where we need a whole bunch of different hash functions. And so you can select, say, the letters A, B, C, D, E, F, G, or the numbers, like a bunch of numbers, and they can be effectively arbitrary if they're large enough and they have a bunch of kind of, they shouldn't be integers, they should be large, kind of like large doubles. They have lots of kind of 0-1 flips of bits in them that look kind of random. You can generate them randomly once at the beginning, and then they become deterministic. So if you want to do your own, this is a simple way to do it. I just want to mention it. But try and using built-in ones in a language will make your life a lot easier. And then there's this modular hashing. This is h of x equals x mod m. Don't use this, okay? So don't. Okay, I just wrote this up there. If you look up hashing, and people often use something like this, and it can run into some problems. Okay, so, but you might accidentally, this might be the first thing you think of. This can run into some issues. I only put it up here to tell you not to do it. Okay, and I think when Sunipa gave a lecture, she misspoke on that, so I wanted to correct that. Whereas with the SHA-1, if you don't use a salt, if you don't put something in here that defines the hash, which is the same, plays the same role as this A here, bad things might happen, right? One of the classic built-in hash functions, I think is for Python, like Vivek was telling me about this, like the words can and, or two very kind of common words, end up hashing to the same spot commonly, the same output in a common hash function if you don't use a salt. If you use that without a salt deterministically, you get all these collisions and your classifiers work 10% or 2% worse than they would otherwise. So put something random as a salt to everything in your hash function, and this will also allow us to define multiple ones. Okay, so I just want to clarify that, yeah.
Why is like a random salt used rather than like identifying a very good salt and using that one?
So, I mean, the issue is that essentially a very good salt might be putting no salt in, right? So this SHA-1 hash function by itself, it has nice properties. Basically, it looks like it's random. You put strings or whatever or numbers in there, and it looks like things collide with roughly half the time. But it's deterministic, right? So if you find two numbers that collide, they will always collide, right? So, you know, if you use this once and you don't know this ahead of time, this probably is fine. But if like there's a hacker who knows this and knows you're using this hash function and they know these things collide, they can build weird data sets that cause your algorithm not to work well. Something like that, right? Or we're going to do some randomized analysis and we want to say the probability that they collide is small, and this will have nice properties. And we'll see these, I think, starting on Monday next week. And we'll need more than one hash function. right? So I don't know what a good salt depends on my data set, but I want to choose these maybe before I start looking at the data, right? I want to write the code, and then as the data comes in, I just want to throw it through the code.
So you don't want the results to depend on the salt?
They will depend on the salt, right? But they're going to depend on it in, essentially, if I chose the salt randomly, they'll depend on it in a random way. And I'll be able to describe how well it works probabilistically. And I'll say with high probability, this is going to work well, right? Where if I chose it deterministically, it either works or it doesn't work, right? And so, you know, eventually something will go wrong probably. This is kind of a tricky concept, so hopefully we'll see it in action next week, Monday, and this will start to make a little bit more sense. Okay, great. Okay, so so let's see. So okay, I'm still figuring out the most efficient way to use this. Okay, so what do we want to talk about today? We want to start talking about distances between so some documents. So think of these as text documents. Okay, and so we'll talk about the specific way we'll approach this is a distance called the Jaccard distance, and we'll use this technique called k-grams to take our text documents and turn it into something that we can compute a distance of. Okay, so the sort of questions we want to ask are say given two homeworks, you know, did they plagiarize, something like that. Okay, so is one homework a copy of another one or close to a copy? Are they close to copies? Right, so you know, I don't know if you know this, but Canvas has a built-in thing I can turn on that looks across all the homeworks and says, are these homeworks, are any homeworks really similar to each other? Or if I pass in code or something, and this is kind of a pretty standard trick that a lot of professors use to check to see if things are plagiarized. And it's kind of built on basically the techniques that we'll start talking about today and over the next couple lectures. So another place this comes up. So given a keyword like a search in so like Google, which web pages are so similar to this keyword, right? So if I put in the keyword, so like data mining, which web pages on the web say have useful stuff so about data mining, or are two pages so duplicates, right? If you look on the web, if there's a really popular page describing some concept, someone who wants to get clicks on their page may copy that page and put it on their page. So, you know, this happens and there's an issue of plagiarism again, but Google doesn't want to necessarily say who's plagiarizing who, but they want to say, I don't want to show you both of those pages in the top 10 list of search results. So I want to filter out things that are too similar in the search results. So how do I do this? Right? And then, so then with emails, so is it spam? Okay, so how most spam filters work at a very high level is that they have this corpus of known spam emails, right? And so then a new email comes in, and and so there's some algorithm that says, is this close to any other email that I know is spam? And if it is, I'll probably mark it as spam. The spam filter will flag it, or it doesn't even make it into my inbox. Right? So these are all the sort of questions that we want to answer. Okay? And so in order to do this, so the key trick here is that we have some document. It could be a homework, a web page, an email. Okay, and we're going to kind of take it into some text, and then we're somehow going to map it to some point. I'll use point kind of generally in some kind of space. Okay, so this is kind of an abstract concept, but I'll make this concrete in a few different ways. So this text document gets mapped to some point in some space where I can define distances, right? And then I'm going to have another text document here, another email, and I'm going to somehow, and so what we're going to do is we're going to ignore things like hyperlinks and images. We're just going to look at the text, and then we're somehow going to map this text into another point in the space, right? And so then once we have it in this space, what we can do is we can look at the distance between them, right? So say this is a point P, this is a point Q, then I can look at some distance between P and Q. And if this distance is small, I'm going to say these documents are similar. If it's large, then these documents are not going to be similar. If they're really, really close to each other, or they're exactly the same, I say this might be an exact copy. It might not, depending on my transformation step here. Okay? So this is kind of the key picture here, right? In order to take something like a document, I don't know how to say, just looking at two web pages, maybe someone changed the background color or made some small changes. I want to somehow get the relevant information. Right, so this is somehow, I'm saying, is the relevant info. And then I want to take this relevant info and map it to some space that has some well-defined notion of distance, or maybe a similarity instead of distance. And then I can measure the difference between them. If I just have two web pages, I don't necessarily know how to measure how similar these are in a constructive manner. Okay, so one of the key hidden things in data mining and a lot of data analysis is you need to do some modeling here. Okay, so this whole step of going for here is this modeling step, where you need to decide what is relevant and how do I map it into something where I can then measure distances. Okay? And there's a lot of choices here. We're going to talk about distances where these points P and Q are going to be sets. Okay, so that's what we're going to talk about the next couple of lectures. What's even more common is that these are high-dimensional vectors. So the common setting is that P and Q are going to be these high-dimensional vectors. That means that P is going to be P1, P2, up to some PD, where I have D coordinates, and then I can do something like take the Euclidean distance between these points. I can think of them as vectors in a high-dimensional space, and I take the straight line distance between them. Okay, and we'll talk more about these sorts of distances a little bit later in a couple weeks in the semester. And variance on, do I want to take the straight line distance or something else? There's lots of choices here. But what we want to talk today about is where, today, where P and Q are going to be our sets. Okay? There's a very nice modeling of text that maps it into a space of sets. And then we need to define a distance. We use the Jaccard distance. Will be a distance between sets. Jaccard distance. Okay? So the outline of the rest of the lecture today will I'll be talking about how to take text, what is the Jaccard distance, how to map text into sets, how to apply the Jaccard distance onto these sets, and why this makes sense as a distance for documents. Okay. This is going to be something that at first glance is not going to look like it's very efficient to compute. And so the next couple lectures after this will be how to make this efficient. Okay, so this idea of this modeling of text as sets and using Jaccard distance is what the very first search engines were built on these ideas. So pre-Google, there were this search engine, so Alta Vista. Who's ever used Alta Vista search engine? Kind of dates me a little bit. So this was the really cool thing when you could first kind of search for stuff on the web, and this sort of technology is what made this possible. Okay, so modern stuff, we'll talk about how kind of modern Google search engine works nowadays, and it's built on a lot of these concepts, but there's more bells and whistles we'll need more ideas to learn about. We'll see later on in the course. Okay. But this is still used in a lot of production systems for dealing with text, these ideas. Okay. Okay, so questions? Okay, so before I talk about specifically the Jaccard similarity, I want to talk about this idea of sets and distances first, right? So a set is, okay, first I need to say, a set is a collection of objects. Okay, and so we're going to kind of use this fairly abstract notation here, right? So I'll just use like letters or numbers as elements of the set, right? And I'll use these curly brackets to describe it's a set of objects. So that means that this is equivalent to A, B, C. The fact that A occurs twice it doesn't make any difference. I just see what elements are in the set or not. It's also, I can change the order. So CBA is equivalent to ABC as well. Okay? But this is not equivalent to A, B, right? It's missing C. It's not equivalent to A, B, C, D. Okay, so you've all seen sets before, but just to make the notation crystal clear. Okay, so the next kind of concept that I want to make clear is the difference between a distance and a similarity. Okay. So probably a lot of you have heard the term distance before, and we'll talk about metrics, which are a special type of distance a bit later on. But I'll typically say a distance between two objects A and B is D of AB, and a similarity is A and B. Okay. So just a reminder, I think I said in the video, but this class will have a fair amount of mathematical notation because I want to describe stuff in the way that it's discussed. So we'll be doing this in class, but I'll try and kind of introduce stuff, but it'll, I'll have all this notation up here, but hopefully it clears as we go. Hopefully you'll see it's very powerful to get the notation right. If you don't get the notation right, it's really hard to describe some of these concepts. So I'll spend time to make sure we get the notation for this stuff right. Okay, so just to be clear, often I talk to even like lots of people who don't kind of really think about the distinction between these. But if the distance is, if this is small, then it means A and B are close. Where if the similarity is small, it means that A and B are going to be far from each Okay, so these are kind of like opposites of each other, and similar if this is large, then these are far, and if it's large in the similarity, then these are going to be they're going to be close, right? So think of a similarity. So typically, if the distance is 0, then this typically implies A is either the same or almost the same as B. Where if the similarity is 1, it usually means that A is about the same as B. Sometimes it means they have to be exactly the same, but there's lots of variance of these things, so they're not always exactly the same. Okay, so these are kind of, again, different from each other. Sometimes the similarity can be really large. It can be much larger than 1. It can be a very large number, and that means they're very similar to each other. It's not always so clear. But so the distance is often between 0 and infinity. This is a fairly common setting, but sometimes it's, say, between 0 and 1, and where similarity is often between 0 and 1, right? Where this is the case where they're the same, and this is where they're totally different, okay? Whereas the infinity is where they are totally different, and this is the same. Okay, so often a similarity has the property, and this is kind of a little bit loose, that it pays attention to things which are close. If things are starting to get far, it's not as meaningful anymore. The same properties are true of distances in many scenarios, but it's less clear that that the far things really start to lose their meaning. Where with similarities, this becomes true. If like everything that's where the similarity is below, say, 0.001, those might be indistinguishable with each other. It doesn't mean one's better than the other if they're both really, really small. They just start to lose their meaning when things get very close to 0. Okay, there are a couple of ways of going back and forth between these. Let me make a little space here. There are typical ways of kind of moving in between these. So you can either make, if I have a similarity, I can often define the distance in one of two ways. Either 1 minus the similarity of A and B. And so in the case of Jaccard, this is going to make sense. And this makes sense in the setting where the similarity is between 0 and 1. Then the distance would also be between 0 and 1. There's another common way of doing this where it's basically the similarity of AA plus the similarity of B minus 2 times the similarity of A and B as the square root of this whole thing. Okay, and so this is common with where the similarity is the dot product and this is the Euclidean distance. Then the similarity is not restricted in here. It can be any large number, but the distance is 0 to infinity. So these are not hard and fast rules, but these are just kind of general guidelines of how to think about these. Yeah.
Would the similarity of AA just be 1? Or
not always, right? So in the general case, yes. Right, in the case we'll talk about with Jaccard, that'll be the case, and that's why we'll use this version. There are other versions where you'll use a dot product as a similarity between two vectors, and then it's not restricted between 0 and 1. These are not kind of strict rules, but these are kind of when it's more natural to think about a similarity, it's usually in this setting. When it's more natural to think about a distance, it usually looks like this.
And these are like the Jaccard.
So the Jaccard will think about the similarity, and it will have these properties. Okay. With Euclidean distance, we'll think about usually the distance, not the similarity, which is the dot product. And we'll think about it in this. Okay, so these are just kind of, when you think about distances, it usually looks like this properties. When you think about similarities, it usually looks like this. And that's kind of a guide. Yeah.
D lowercase is for Euclidean distance and D uppercase is.
I'm using kind of talking in general about distances.
Oh.
So we'll see lots of examples of different distances. This could be lowercase. I'm sorry.
Oh.
Yeah. Yeah. Let me make this lowercase here.
Oh.
Okay. So, this isn't hard stuff. I just want to kind of thinking about these two things. Okay, so let's see the Jaccard distance. Let's see what this object is here. Okay, so the Jaccard distance. Okay, and so I'm going to have an example where I have two sets. 0, 1, 2, 5, and 6. 0, 2, 3, 5, 7, and 9. Okay, so there's no 8. That's fine, right? It's not in either set. They both have 0 in them. One of them has 1. The other one doesn't have 1. Okay, so these are not exactly the same sets, but they have some similarity between them. How do we measure the similarity? Turns out there's a ways to do it, but a very common one is called the Jaccard similarity, or the Jaccard similarity. Okay, and so the Jaccard and B, so these are general sets in this definition now, are going to be A intersection B. So this is the cardinality of A intersection B. That's the size of the set of their intersection divided by the size of A union B. Okay? And this will be between 0 and 1. This has to be because the intersection has to be smaller than the union, right? So I'm dividing by dividing through by something which is larger. The denominator is larger than the numerator, so it has to be less than 1. They are always positive, so it has to be greater than 0. As the union, as long as both sets are not empty, this is well defined. I'm not dividing by 0. Okay? If these are both empty sets, then I just define this similarity as, I can define it arbitrarily as equal to 0. Maybe I define as 1. We can define as 1 or 0. It doesn't matter so much. Usually, if these are data, A and B are data, they'll never be empty, because that doesn't make sense as data. We don't have to worry about that case so much. Okay, so let's go see what this example is. If I look at this example, the intersection of A and B is 0, 2, and 5. And the union is 0, 1, 2, 3, 5, 6, 7, 9. Right? Okay, and so this is equal to 3. That's the size of the set on top, divided by 8. Yeah, so 3 divided by 8. And I get a similarity of 0.375. Okay, so I've defined a similarity between them. If this, let's see, if I put 3 in the top set A, there's no 3 in there. If I added 3 into the top set, right? If I took the union with 3, they should be more similar, right? Because 3 is in B, so the union is going to stay the same, but the intersection is going to increase, so that would be 4/8. The similarity would increase. Right? If I added an element 8 into the bottom set, the intersection stays the same, but the union increases. So the numerator, or so the denominator would increase. It'd go from 3/8 to 3/9, and this would decrease. They'd be less similar to each other. Right? So this, intuitively, this makes sense as a similarity, right? It's capturing how similar the sets are. And one of the nice things about it is that, I don't need to know what is the domain of all the numbers, right? I can be from 0, it could be only the numbers I could be allowed are between 0 and 10 or 0 and 100. I didn't need to know that in order to calculate that. Right, so that'll be an advantage of this type of similarity. Right, and then the Jaccard distance between A and B is 1 minus the Jaccard similarity. Okay, but we'll mainly be focusing on the similarity. Okay, so this, let's see what I have. Let's, okay, we're not to that yet. Okay. Okay, so this seems to make sense as a similarity between sets, right? Now, so I said back here that there was a modeling choice here, right? I'm going to take the documents into text and I'm going to somehow convert them into sets, and then I'm going to define a distance between them, and I can choose the Jaccard distance. But once I have them as sets, there are lots of other possible distances I could use. There's lots of different types of distances between sets. So I just want to kind of give a general sense of what these are like, just so you're aware that there are many types of distances, and you have to choose one. And there's not always a right or wrong answer. There are some that are going to have computational advantages, and some that are going to have modeling advantages. They're going to make better sense than the other ones. You're going to kind of assign meaning to what they mean in a different way. Now, the Jaccard similarity is a very popular one, and it's a good default, but there are other ones as well. So, so let me list a couple of these other ones here. So the Hamming similarity, we'll call this Ham A and B. So this is going to be equal to A intersection B divided by A intersection B plus A the symmetric difference of B. Okay, and this is, hold on, no, I wrote down the wrong one. Sorry about that. Okay, so this is going to be equal to A intersection B plus A union B, so the complement of the union, A intersection B plus A union B, the complement of the union, plus A symmetric difference of B. And you can rewrite this as 1 minus A, the symmetric difference of B, divided by the size of the domain, right? So there's some domain that all the data sets come from, and that's of size n. So that's going to be just, this is just A, the symmetric difference of A and B, divided by n. Okay, and so if you don't remember what the symmetric difference is, if this is a set A, this is a set B, then the symmetric difference is anything, this is a symmetric difference of B. It's the stuff that's in A or B, but not the union. Right? And then there's going to be, think of there's some overall domain here of size, so some overall domain.
So it's like an exclusive OR.
Yeah, that's right. So it's a set operation of that. Okay, and so with the Hamming similarity, you've probably heard of the Hamming distance, and if you have bits, this is just the 1 minus the Hamming distance. This one requires you to know the size of the whole domain, where the Jaccard distance didn't need to know that. But when you're looking at bit strings, and so you know that because everything is a bit string, you know there are n bits, then this is a common similarity, right? But this is another choice. All right, let me write down another one. The Anberg similarity. We'll call this Anberg A and B. This is going to be equal to, let me write it this way, A intersection B, the size of the intersection B, A union B plus A, the symmetric difference of B. Sorry, it's a plus. Okay, so this looks a lot like the Jaccard distance, but I've got this extra symmetric difference term on the bottom here. Right, so before I just divided by the union, now I'm weighting I'm adding to the denominator and divide by something larger. If the symmetric difference is larger, I make this smaller. So the denominator is still less than the numerator, so it's still between 0 and 1. They're both always positive, but it's a different and it's a well-defined similarity. And there's some context where the Anberg similarity is the common thing to use for some versions. I'm going to write one more version down. It's called the Sorensen-Dice similarity. I'll just call this, sometimes it's called the dice score between two sets. This is often used if you're doing like, say, classification of two data sets or clustering of two data sets. How similar are these results? This is defined as A intersection B divided by the size of A plus the size of B. Okay, so in some context, this is the kind of the default measure of similarity between two sets. Okay, and the intersection will be no larger than either A or B. So twice the intersection is going to be smaller than the size of A plus the size of B. So again, it's between 0 and 1. Everything is positive, so this kind of checks all the boxes it's supposed to check. And this is another valid similarity. Okay, so we have choices that we can use, and these are modeling choices. There's this, I want to quickly write up, there's this general form of a similarity. I'll call this X, Y, Z, Z prime. Okay, and so if I write similarities in this general form, X times A intersection B plus Y times A union B complement plus Z the symmetric difference of B. Okay, X plus, so far the numerator and denominator are the same, but I put a Z prime now at the bottom here. Okay, so I have, this part is the same, this part is the same, but this is Z and Z prime of a symmetric difference here. Turns out all of these similarities, including the Jaccard and a couple of other ones, common ones can be used, can be written as in this general form, where I specify a specific value for X, Y, Z, and Z prime. For instance, the Jaccard similarity is going to be, so for instance, a Jaccard similarity is equal to S1001. Right, so if I set X to be 1, Y to be 0, I ignore this term and this term. z to be 0, so I ignore this term, z prime to be 1, then I get x a intersection b in the numerator, so a intersection b plus a symmetric difference of b. The sum of these two is the union. Okay, so I recover the Jaccard similarity. So this is kind of a general form, and there's kind of if it looks like this general form, we can kind of, it's going to kind of generally make sense as a type of similarity. So there are lots of choices by just choosing x, y, z, and z prime parameters. Yeah.
So you said that the dice similarity formula is usually, it tends to be the default for the distance between sets, or the similarity between sets. So why wouldn't it be Jaccard? Because Jaccard seems more intuitive.
So this dice occurs. There are certain domains, like I've seen in a lot of image processing papers, or things where they want to say there are two images there's a bunch of pixels of some image of like someone's liver, and I want to determine which pixels are part of the liver and which are not part of the liver. And I wanted to say, here's the ground truth, and here's the and here's what I found. How similar am I to the ground truth? The thing used in a lot of these papers is the dice similarity, for whatever reason, right? The thing used in analyzing text is often the Jaccard similarity. The Jaccard similarity will have this nice feature called min-hashing we can apply on it in a pretty straightforward way. I think you can apply it on dice. I have to look this up, but I'm not sure about it. And just the first papers in the area use dice instead of Jaccard. And so now that's what everyone uses for better or worse, right? But there's not necessarily a good reason for this. And so a lot of this modeling that comes in, and choices as a data scientist that you will make, and that will affect the outcome of your decisions. So there's kind of this is your introduction to some of the black magic. Okay, and I won't always have answers, but I'll try and tell you where it is. Okay, so that'll be the goals for the course, yeah.
Is it always dependent on the size of the set, or it is dependent on the value of the set as well? Because it's quite possible that there is a set 49, 50, 51, another one is 52.
Yeah, so in sets, the idea is that the numbers don't matter so much. They're representative of something, right? They could be representative of IP addresses, or they're different words, right? We'll see an example with text soon. And each element, potential element in the set, could be a word. Now, the fact that I have, let's think of two words next to each other in the dictionary. Cam, like a webcam, and can, like a can of corn, right? The fact that those alphabetically are right next to each other has really no bearing that they mean completely different things, right? So the fact that the numerically are similar to each other in the set notation, this shouldn't matter. Okay, so we're going to see some other stuff later on in the semester where concepts that, like if I say a can or if I say bucket, can and bucket roughly at some level mean the same thing. So the fact that I see one word instead of the other those are kind of replaceable with each other. And we'll see things later on in the semester where we'll be able to kind of compress them into a similar representation, right? But right now we're going to ignore that. The set notation does not capture the information, right? So when you go back to the modeling, right, you're going to make choices of how you do this, and you have to be cognizant that when I go to a set representation, I'm not capturing this information. There are other representations where I will be capturing stuff like this. And so these are the sort of things that hopefully you will learn throughout the class, and you'll start to be aware of these questions. So that's a great question, right? But this is something that's not captured at this point. Okay. All right. Okay, so, okay, cool. So I think you kind of get the Jaccard similarity, which is kind of the main one we'll talk about, but that is a choice. That it's a modeling choice that you've made. Let's see, how do we get this from text, right? This is what I promised, that we would get this from text. And so I've got some slides to kind of make this a little bit more efficient, right? So we're going to go through an example. Okay, so how how we're gonna, here's an example piece of text, and I want to convert this into a set. Okay? And the idea is, I'm going to focus on something called the K-gram technique of turning this text into a set. Okay? And so there are some variants on K-grams. Again, these are going to be modeling choices. We're going to start with the word level K-grams. I think this is what, yeah, we'll start with the word level K-grams. And so if I have a 2 word gram, then what I'm going to look at is I can see all the words, and that tells me something about what's going on. But I want to capture, you know, not just which words are in there, but which words are next to each other. This will tell me a bit more about it. So I'm going to break it into set by saying that each pair of consecutive words is going to be a set. Right? So I'm going to get, and this is a 2-word, where I'm looking at 2 consecutive words. So K is a parameter. In this case, it's 2. I'm going to get I am. This is going to be one of the elements. So I'm going to get, actually, this is going to be an object. So I'm going to create a set from this. So I'm going to think of stringing this all together as one document. The first one is I am. The second one is going to be am Sam. Right, so I've repeated am. I've used that twice. Right, I've gone from, right, and then the next one here is going to be Sam. Okay, and so I can keep doing this, right? And I'm not going to write all these questions.
You said they were objects, not sets, which is why we duplicated set.
Well, I'm creating a set, right? I've got my curly bracket here, I've opened, and I've started putting these elements into it. So this I am.
So the 2 word grams are objects, though.
Yeah, so this is an element in my set. Right? Before I was using numbers or a single letter instead. Now I'm going to write down this is I am. Now in practice, these are going to be kind of a messy to keep track of, so I'm going to use a hash. So I'm going to take this, I'm going to throw it in a hash function, and it's going to turn it into a single number. And then I can just pretend they're numbers again. All right, so this will be the power of what we're going to use, one of the ways we're going to use hashing. And we'll see that on the next lecture on Monday. I'm kind of not just doing that, but a bunch of other cool stuff you get with the hashing. Okay, so let's see, if I keep doing this, this is what happens if I did it with k equals 1. Right, so I started with I am Sam, but then I don't include Sam again, right? I only have it in here once. It's a set, so each object, I don't count duplicates. Okay? There's another version of this we'll talk about either at the end of the lecture today or in another lecture where you can count. I see that Sam occurred 3 different times in this document, so I want to keep track it occurred 3 times. Here I only say it occurred. I don't keep track of how many times it occurs. And then with k equals 2, I can see I have the I am Sam, Sam I, and so forth. Right? But the I am, which appeared here, is not appearing again in this spot. Right? Right? So it's repeated, so I only need to keep track of it once. Okay, so this is the word K-shingling, or K-grams or K-shingles of this text document. Okay. Okay, so this is, I said this was with words, but I can do this with characters as well. Right, so let's look at this shorter sequence where I have I am Sam, and I can do this with the individual characters, right? So I have, and this is with k equals to 3 and characters here, right? So I have I, A, M, and that goes in the first set here, right? And you'll see that this I, A, M appears again here, right? So but I only count it even once. Right, and here's the answer with 4 characters. I get something slightly different. Okay, and okay, so before I move on, yeah, I'll pause because there's, if I look at this, there's a lot of choices I secretly made here. There's a lot of modeling choices I, again, secretly made. Right? What are these other modeling choices? So there was these word, I showed examples of the word versus the character. Did I do shingling on the words or the characters? And what is the value of K? Right? So I made 2 choices already, and I showed a couple of examples, right? So those were choices I made, and I did not tell you what was the right one to do. Right? Should I use word or characters? So what? So the characters, yeah. So I was surprised by this. When I first learned about this, I thought, oh yeah, the words will capture kind of so much more intrinsic information of what's going on here. But the character seems to be a bit more effective in a lot of modeling contexts. So sometimes you want to use words, but like the characters it inherently captures what's going on with the words as well. It's just at a finer grain. So if there's a common sequence of characters common to words, that's going to show up in your charactergrams as well. Yeah.
In these character sequences, are we also omitting punctuation?
Good. So punctuation. I've removed all the punctuation. There was a period at the end of Sam, and I haven't included that. That's a choice. I could include that. Right? Sometimes you might want to do that.
The white spaces.
Yeah, so the white space. Right? I've removed white spaces. Okay, so should I include white space? Maybe I should include white space. Right? I haven't here, but I could have. Right? These are all choices I made, right? And if you see different implementations of this, people make different choices. Sometimes they will include white space because that tells you the separation of words. The period at the end of a sentence tells you, okay, this word appeared at the end of the sentence, and the next word, if a k-gram starts with a period, that's the start of a sentence. That might carry more significance to it. Or if there's a question mark, that means that the thing coming before it has to do with the question. The fact that there is a question mark in there means that this is a question that's being asked. Right? These are all things that might be helpful. Yeah?
Are these 2 sentences part of the same document or different document?
Yeah, so, in this case, I'm treating them as the same document. Right? Well, I'll show an example next where I'm going to treat each line as a different document just to show how Jaccard Similarity works. Right? But in this example and the previous one with the wordgram, I treat them as the same document. Yep.
Also character case.
Case, yes, good. So capitalization. Right, so I've turned all the S's in Sam to be lowercase here. Now I didn't need to do that. If I kept that S was uppercase, I would know that this is probably a name, right? Or is there some proper place? This tells me more. But it also increases, when I add white space or punctuation or capitalization, it's increasing kind of the space of all the sets, right? So it's less likely that I have an intersection. Right, so let's say that a punctuation came because it was at the start of a sentence. There aren't any good examples here, right? But say I started a sentence with the word pizza is my favorite food. I like to eat pizza, right? So the first time pizza occurred, it was capitalized. The second time it didn't. Now with the capitalization, I don't know that these are the same word anymore. Right? So it's not always advantageous to add the capitalization and these other punctuation and spacing into this. Right? So these are choices, and there's not a right or wrong answer. What I can tell you is about the choice of K. Typically, the shorter the document you're dealing with, you want to have a smaller K. Okay, the smaller the documents, the smaller the space. For instance, if you're dealing with tweets, these are really short documents. You want to have a pretty small K, and you probably almost definitely want to use characters instead of words. Right? Because people merge words together sometimes. They might drop the white space, they might not. They might use apostrophes, they might not use them. They might use emojis in there. These are characters. There's lots of these issues. Where if you have a longer document, like there's like a corpus from like Reuters or like New York Times where they have long articles, and there's a very formal language that's used, then it might be useful to kind of keep track of capitalization because you know it's going to be consistent. Or with kind of using words instead of characters because you have more to work with. So it might make sense to use words instead of characters. Right? So the longer the document, you might want to use a richer representation. The shorter the document, you want to use kind of a simpler representation. Okay, so that's a general guideline, but where to draw the line, how to make decisions on each of these, there's no right or wrong answer. All right. Okay. So let's go through an example now with k-grams and with Jaccard similarity. Okay. So in this example, as you were asking before, now I'm going to say each of these lines is going to be a different document. Okay, so I have 4 documents, D1, D2, D3, D4. Okay, it could be more complex, but this will illustrate what's going on. And notice, in order to get this to work, I picked some text which is reminiscent of Dr. Seuss book. There's a lot of repetition in it, right? If I don't have this repetition, I'm not going to see similarity typically on really short documents like this, right? I might not see it otherwise. Okay, and I'm going to use word k-grams with k equals 2. All right, so I'm going to use k word grams, right, with k equals 2. So I'm going to convert these documents into these k-grams with word equals 2, right? So I am Sam becomes I am and am Sam. Sam I am is Sam I and I am. And notice that the I am appears in both of the first 2 lines. Right? Okay, so all right, so let's see. So let's calculate the Jaccard similarity between these sets and see how similar they are. Forget how much I have. Right, so the first example, the first 2 lines between documents D1 and D2, right, the first 2 lines, this Jaccard similarity is 1/3, right, because the one intersection is I am, and I have am Sam and Sam I complete the union, right, so I'm getting 1/3. Right, what is the Jaccard similarity between document D1 and D3? 0, right? There's no intersection here. Good. Did that. Let's see. How about D1 and D4? It's 1/8, right? They're going to be I am is repeated, and there's 7 on the bottom sets and 2 on the top with 1 intersection. So the union is going to be size 8. It's going to be 1/8. Right, so this says that D1 and D3, I don't see any similarity. Right? There might be some words that are repeated, but none of the 2 k-grams. And D1 and D2 are somehow more similar than D1 and D4. Right? Both D1, D2, and D4 all have the same the same one element in it, I am, but because D4 is a larger set, it's less similar to D1 than D2 is. Right? So it's got a lower similarity with D1 than D2 had with D1. Right? So this intuitively makes sense. Right? Okay, let's look at the rest of them. D2 and D3 also have no similarity. D3 seems to be kind of the outlier here. D2 and D4, they have 2 out of 7. They both have SAM IM in them, right? So and so the intersection's a bit, the union's a bit smaller, and so this is a bigger similarity than D1 and D4, right? It's pretty significantly different in this small data sets. And then D3 and D4 have the similarity with the I do not like, right? So it's got 3 things which are similar out of 11, and this is, even though they're longer documents, they're about as similar as D2 and D4. These numbers are roughly the same. Okay, so it works with documents of different lengths, and it kind of, I can say 2 smaller documents are similar or larger ones are similar because it doesn't need to know how big the whole set is. So it's a pretty kind of flexible similarity that has a bunch of these nice properties. All right, okay. So this kind of makes sense as a measure between these documents. You can do this. So now if I told you, to implement this, to say take some documents, do some version of k-gramming, right? I would have to specify, or you would have a modeling choice to do the character grams or the word grams, to do white space or punctuation. You could turn these documents into sets. This might include some messy parsing, but I bet you could figure out how to do this. And then to compute the Jaccard similarity and see which ones are more similar to each other. Okay, that seems like, I feel like you guys could all do this by the end of the lecture. You have to work out the coding, but I bet you could work that out.
So earlier you brought up the point of like synonyms, so like word
Yeah.
set. So this can't handle that at all, right?
Right. This does not make any attempt to handle that.
Okay.
Right. If I know some synonyms on the word level, I can start to say, I could say those. I can map those to the same objects.
Oh, when
right.
you make the sets.
Yeah, I could try and do that. That's rarely done with the k-gram. That's a bit harder to implement in this setting, and it's usually ignored at this level of modeling. Now I might map this into do some like PCA sort of stuff on it later on. That's going to kind of detect this automatically, and we'll discuss some of this later on in the course. For this sort of modeling, I don't have a great way of doing that.
So I'm just trying to tie in different concepts. So we could theoretically have a hash function that takes synonyms, hashes them to the same value, and then use those values in sets, and then we had unique values for synonyms of words.
Yeah. Right. So let me tell you about another modeling approach, which is going to be a bit better at handling these sorts of types of modeling. Right. So I wanted to tell you one more concept today. Let's see. So this is called the bag of words model. Okay, so this is not going to kind of map stuff to sets. This is going to map stuff, documents to vectors instead. Okay, and so we're gonna come back to. We're going to do a few lectures where we're going to deal with sets, and then we're going to mainly work with vectors for most of the rest of the semester. So let me just give you a preview of this. So if I have the word Sam I am, right, is my document. This is then I want to keep track of which words are in this document. And so the way to do this is I'm going to map this document. I'll call this D1. I'm going to map. I'm going to go from D1 into some point P1, and this is going to be in some very high dimensional, so Euclidean space. So m-dimensional Euclidean space, which is going to mean that this P1 is going to be a vector. Let's just call this P, just so I don't have to worry about indices, double indices. So P2, P3, up to Pm. Okay, and so Pi is going to be the number of occurrences of word I. Okay, so the idea here is that I've got this really, really super long vector where each possible, every entry corresponds with any word I might see in the dictionary. I might restrict to some uncommon words maybe I don't keep track of, right? But I could think of this word is P2 is Sam, so 2 equals Sam, 3 equals I, and say 5 equals to M. Okay, and the vector keeps going, but if I map this word down here, it's going to be equal to 0. P1 is something else. Sam occurs once. I occurs once. So this word doesn't matter. Am occurs once, and then the rest is zeros. Okay, and so if it was instead Sam, I am Sam, right? So Sam occurred twice, right? So if instead Sam occurred twice, then I would keep track of that. I would change it to be 0, 2, 1, 0, 1, 0. Right? So if Sam occurred again, I would increase the counter here. So in this way, I keep track of every word individually. I typically don't do this by doing charactergrams or wordgrams. I usually keep track of individual words, and then I keep track of these word counts. Okay? So in this setting, I'm keeping track of individual words. It's a little bit easier to say these two words mean roughly the same thing. I'm going to keep track of them in the same counter. Right? If I know that ahead of time, this is easier than if I'm doing charactergrams or if I'm doing kind of 2 words or 3 words together. That's a little bit harder to keep track of. Here I can just map them together. There are also things we'll learn later in class where we do PCA. This will more naturally in this setting will be something where we can determine these words tend to occur together a lot, right? And we'll have ways of learning this. So something I need to I'll cover in another lecture is these word embeddings, where instead of taking a document to a point, we're going to have a lot of documents, a lot of text, and each word is going to be a point. And we're going to map each of these to vectors, and then 2 words are going to be similar in the space if their distance is small. They're going to be next to each other in the space. They're going to have similar meaning and uses. And there's a lot of other kind of cool information coded in here. So we'll talk about. I don't have a great part in the notes about this yet, but I plan to add this into a lecture later on this semester. All right. So this bag of words model is an alternative. You would typically not use the Jaccard distance. And it won't work because I don't have sets anymore. Because if I have a 2 here, this is no longer a set representation. But I can use Euclidean distance, and that turns out to be the right thing to do. And that generalizes naturally to high-dimensional vectors. So one more bookkeeping before we go. There was a little piece of the lecture on Wednesday which we didn't get to because I think I pack too much in there for SANIPA. There's a part on the central limit theorem and the Chernoff-Hofting bounds. And the bonus question in the homework is about this stuff. So you don't have to do the bonus question. If you want to say amount of points per time, it's probably not worth it, but it's some interesting stuff. It's covered in the notes, and I will put this in a later lecture when we have some space at the end of the lecture, so we'll cover this later on. But I'm not sure if we'll cover it before the homework is due, but you can read it up, and if you want to answer the bonus question, you can look at that. And we'll probably tie that in with some other stuff when it's relevant. Okay, if you want to look at example posters from previous projects, from previous semesters, we've got a bunch of them up here. Get some ideas of what some projects have been about. Thank you.
I think he's dropped it.